Okay, so we are wrapping up this problem. We got a picture on the board where we're hoping to convince ourselves that the upper sum using a partition with 3 points, P3, is actually a better estimate than using a more refined partition of 4 points. So this is a step function, and notice that we can move these endpoints between the steps up and down anytime we need to without adjusting the value of the integral by theorem 6.5. So we can move them up and down to make constant segments anytime we want, and that's how we actually evaluated the integral. We got the exact value here, which I've written on the bottom of the board. Now the thing of it is, if you use a partition P3 whose elements are exactly at the edges of the steps, then the big MIs, the big M, and I've written it here, the big M1, big M2, and big M3 are just the values of A, B, and C, the Y values of the function, of the steps. So you actually get that this thing, UP3, is the exact value of the integral. Okay? But UP4 of F, which would involve some different points, right? UP4 of F would be like, here, here. No, sorry, I'm starting at A. It'd be here, 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 and here, right? Now, for example, on the second subinterval, right, the big MI is still A, and that gets multiplied. That's actually what I'm calling big M2 prime. It's still getting multiplied by the whole width here. So you're actually getting all of this area. And now you are above the graph. You're calculating extra area there. So UP4F is too big, right? It's too big. It's an overestimate. Now, let me ask you another question. Oh, I could make this into a number theory problem. What about UP6? Let me erase my blue. It's kind of confusing. UP6. How's that going to do? How good of an estimate is that going to be? So here's A. I'm just going to get rid of this. Here's A and here's B. We've got X1 and X2. If I do U6, or UP6, 6 pieces to the partition, what's it going to look like?
Would it cut each of the lines in half?
Yeah. You cut the lines that are already there, you make new lines, you make new points. How's that estimate going to be? It's going to be exactly right. It's going to be the same as UP3. Here's the way to think about it. P6 is actually a refinement. A refinement of P3, right? You're not changing the points, you are refining it. And do we have some theorem about refinement? A refinement only improves the value of the integral, right? It reduces any upper estimate and it increases any lower estimate. Well, if UP3 is already the exact value, right, then UP6 is a refinement of UP3, so it can only make this number smaller, but it can't become smaller than the right answer, right? So you're refining a partition that already gave you the perfectly right answer. So this partition cannot do any better than that, right? You can't do better than perfect, right? So UP6 is a refinement of P3, whereas P4, right, is P4 a refinement of P3? No, if you look here, you've got these 3 points. Those aren't the same as these 4 points. We've thrown these points away and put new points in there. Even though we put more points in there, they weren't refining the points we already had. Okay, so you could probably guess that UP9 or UP12 or UP15, any of those are going to include the 3 points, the 3 pieces that we had before, those upper estimates are all going to be perfect. Does this make sense? Awesome. Okay. So that's that. And by the way, everything we did on this problem, we could have done it for the lower sums too. It'd be pretty much the same. Any comments or questions on that one? If not, I have just one more problem, and then I might say a couple last words of wisdom, if I have any left, and then we'll call it a day. Number 5, suppose that f is bounded on the closed interval ab. Of course, that's required if we want the function to be integrable. What I'm going to do is I'm going to define g from the closed interval ab to r via g of x equals, but here it is, this is a little different, supremum of the value of f at any point y where y is between a and x. And then what we want to do is prove that g is Riemann integrable on AB. So let's just see if we understand the problem. The interval AB is right here, and we have some function f that's bounded. I'm not even going to make it, it's not necessarily even continuous, so I don't want to assume that. Let's just say it's some weird thing like that. Okay, that's my function. Actually, for that matter, we're not assuming that f is even Riemann integrable. You could choose f to be, remember that function that's equal to 0 on the irrationals and 1 on the rationals? Well, that's certainly bounded, right? But that wasn't Riemann integrable. But regardless of that, this function g is going to be Riemann integrable. And the reason I want to ask this question is it combines the stuff on Riemann integrability with something a little bit older, which is the idea of the supremum of a set of values. Okay? So what do we do here? If I want to evaluate g of x, what do? I take all of the values of f between a and x, right? And I plug them into the function. So I would plug all these points in, and I would take the supremum value, which would, in this case, be that point. Do you guys understand how g of x works? Everybody confident they understand how g of x works? If you're confident on how g of x works, can you explain why it's going to be Riemann integrable? Let's suppose that is f of x, okay? And I'm going to, what happened to my blue marker? Might happen. Yeah, got it right here. I'm going to draw g of x in blue. So what is g of a? Maybe we don't know how g of x works. We're taking all the outputs of f that are within this interval, and then we're taking the biggest one. So what is g of a? So I'm going to put a for x.
Wouldn't this be f of a?
Yeah, it's just f of a, because look, if you're putting a for x, then y has to be between a and a, so it can only be a, and you just take f of a, which is one number, and the supremum of one number is just itself. So it's just, so g of a is the same point as f of a, okay? With me? Now as I go further to the right, let's say I go slightly over to here, then g of this point, call it maybe a prime, g of a prime is what? Well, it's the largest value of the function f on the whole interval. so far, which would be where? Yeah, f of a prime, it's right here. Okay, and in fact, any point in between, isn't it just going to be following along? Does it do that forever? So let's keep going. It's going to follow it along, follow it along, follow it along. So we get up there. Now as I keep going further, say I go over here. What is g of a double prime? Is it this value? No, it's the highest value that we've seen in that whole interval, which would be where?
Right before the jump.
Right here, yeah? So this point stays up there, doesn't it? What about all these other points? That should be flat. So the blue curve shows me the graph of g of x. Let me ask again, does anybody know why it's Riemann integrable? It's monotone. It's monotone. G is monotone. The idea is that it's monotone increasing. The idea is that as you increase x, you are widening the interval of y values. You're keeping all of the y values that you've already attained or that you've already considered, and you're including even more. So you're making it an even bigger interval, you're evaluating the function on a bigger interval, so the supremum of your values can only go up. Right? Does that make sense? The picture kind of helps. So g is monotone increasing, so therefore g is Riemann integrable by theorem 6.9. Okay, makes some sense? So these are the kind of problems that I like. You know, most of the problems we did today were not excessively, difficult or tricky, but you have to know what's going on. You can't be totally blind coming into it. And that's really my philosophy about all the questions I'm going to write on the test, is that if you know what's going on, right, you should be able to succeed on the exam. I'm not interested in asking you to do something extraordinarily clever or particularly if there's some minute detail that's not really front and center in what we've covered. I'm not going to be asking you about that. I'm going to be asking you about the big things, the most important things, the things you've seen again and again, the theorems that we've used many times, that sort of thing. My advice is going to be to go back, try the midterms again, try the sample final, maybe rework some of the problems from the problem class. You're not going to be able to do all of the homework again, but you might look at some of it that maybe you had some trouble with a particular assignment or something and you just need to kind of get it solid one more time. You might look at some of that. Those are going to be the best things to focus on. I hope I'm leaving you guys in good hands in terms of your studying and you have all the materials you need. And again, I apologize I won't be around here, but I'm really, just view me as I am really around. You just have to email me or call me. I'm definitely happy to answer a question. I don't want anybody to think that you're bothering me. If you ask me questions, if you call me or email me, this is important to me. Like, I've invested almost 4 months now to really get everybody a good understanding of the material. I'd like to see it through to the very end, through the final. So be sure to ask questions, through the email and through phone if you have any. Okay? Does anybody have any questions right now? Any of this stuff? That was it. Those are the only problems that I brought today. We good? All right. Well, we're going to quit a little bit early then. You can go ahead and